Okay. Hello everybody. My name is Clayton Davis. I am the Director of Data Science for Monty, and today we're going to talk a little bit about explainable AI. We're going to talk about some of the state-of-the-art techniques, as well as some of the techniques that we've developed here at Monty, which also happen to be accurate as the state-of-the-art techniques, as well as a little bit faster. So summary-wise, we'll talk a little bit about why explainable AI, why we think we need it. We'll talk a little bit about current self-explanatory models, as well as what state-of-the-art solutions look like for models that aren't self-explanatory. And then we'll talk about what we've been doing at Monty and how that has really helped to kind of push forward the state-of-the-art, make it a little faster, and then we'll conclude with some extra resources for you guys. So at the beginning, kind of just why explainable AI, right? AI has started to proliferate more and more throughout our society and our world. And I can give you kind of three examples real quick off the top of my head of AI that impacts you on a fairly frequent basis, right? Nest thermostats, which many people have purchased now, the autopilots in commercial aircraft that most of us fly on, and the full self-driving beta sitting in Tesla automobiles. In each of those three sort of scenarios, what we have is an AI system making decisions day to day that affect you directly, whether that happens to be affecting your wallet because the thermostat has decided it's going to turn the heat up in the middle of winter, or turn the AC on when maybe you wouldn't necessarily want it to. The autopilots have very definite impacts on you as they are making decisions about how to fly aircraft with live human people on them. And those Tesla self-driving cars, when they have their full self-driving beta engaged, they impact not only you, but the people around you as you're driving along and the car decides it's going to make a turn one way or the other, stop at a stop sign, etc. In each of these situations, AI is being asked to make decisions that impact you, your health, and your finances. And so it's incredibly important for those who build the AI models, as well as the end users of the AI models, to know why the model is making the decision that it's making, so that we can know in the future when the model is being presented with perhaps conflicting data, that it's leaning on an understanding that we would consider to be reasonable in making its predictions. And so if you kind of look at the top of this slide here, you'll see three different results for three different machine learning models that process the phrase, "I hate the movie, though the plot is interesting." And all three of the models actually correctly assess this as a negative movie review. But the first model on the left, the main thing that it held on to was the word interesting. Right? And we know that if we were to be describing a movie as interesting, it could be both a positive or a negative thing. And so that may not necessarily be a model that we would be interested in using a lot, right? The middle model, it managed to get the word hate and to assume that the word hate was the strongest sort of indicator of positive or negative review. And though that's a good sort of underlying tease out of the data, it's not the entirety of the situation, the context for the sentence itself. It's not until we get to the third model where we see that the model was able to both process that you didn't like the movie, as well as the fact that there was some sort of extra caveat associated with it. And so it identified both the word hate as well as the word interesting as being a component of the overall context of the sentence that provided a final result. And so if you were to try to use, if you had to pick between one of these three models kind of in the real world, you wouldn't necessarily want the first two that only focused in kind of either on single words or maybe even what some would argue to be the wrong word. You would say, okay, I've got three models, I'm trying to do predictions. This last model seems to act in what I would consider to be the most reasonable way by taking into account the same sort of things that I would when I was evaluating that sentence, right? Now, likewise, in a world in which we rely quite a bit on computer vision, right, kind of harkening back to the self-driving car, you have this example in the bottom right corner of a wolf a husky that was classified as a wolf. And when we really kind of peer down into why the assessment was made, we can see that the model that processed this husky was actually really concerned with maybe the jawline of the husky as well as the white background. It didn't actually take into account any of the sort of things that you or I necessarily would, the facial shape, the ears, the eyes, etc. And so as we lean more and more into AI as a society to help solve both mundane and important problems, we need to also be cognizant of why that AI is making the decision it's making. And so the realm of explainable AI deals with providing us tools that we can use in conjunction with our models so that we can understand how the models are making their decisions, which allows us ultimately to continue to use those models in effective ways and not have to worry about their behavior in unencountered circumstances. And so a little bit about models that are interpretable in the sense that we can understand what they're doing just kind of on the front end without a whole lot of extra mathematics. There are two that are generally considered to be explainable and interpretable without a lot of extra effort. The first is a linear regression, which is a very simple machine learning model that most people encounter fairly early on, where the decision that's going to be made by the model, which we'll call f of x here, is basically equal to a whole bunch of numbers that are coefficients, kind of weighting values applied to individual inputs. So for example, your Nest thermostat is going to set a temperature for you throughout your house, and the temperature it's going to arrive at is going to basically be this kind of f of x on the side. And then the things that it would take into account as it was calculating what temperature it should be would correspond to the values on the right. That B0, that beta 0 would probably be kind of like the average temperature you enjoy in your home. Beta 1 would relate to how strongly it should consider things like the time of day. Beta 2 may consider, how strongly it considers the time of year, etc. as you go along the line. And so understanding why, for example, that thermostat may be set at 68 at night in the summer, the way that one would go about figuring that out is that they could simply just read off the beta values, and whichever beta value is highest, the input associated with it would be the one that the model cared about the most, right? And so if beta 1 was 6 and beta 2 was 0.3, then the input associated with beta 1, in our case the time of day, would have been the most important thing for the model as it was calculating the temperature for the house. The second, now that's a very easy to interpret model, but it's also a very simple model. A more advanced and powerful model would be a decision tree, where the underlying mathematics is not as easily written out as it was for the linear regression up there, but the interpretability is still there. A decision tree basically looks at a series of variables, say time of day, time of year, and then has a threshold value. And so if it's greater than a certain value, you'll go to the left in your decision tree. If it's less than a certain value, you go to your right. And so maybe, are we in summer? Yes, we'll go to the right. Is it daytime? Yes, we'll just go over here to the right too, until eventually you kind of get to the end of that tree. So if you want to know, regardless of what the decision is that the decision tree makes, if you want to know why it made that decision or how it came to that decision, you can always go back and just simply follow the path of the tree. And so these two models are fairly simple in their design and their interpretability for humans. And so when the models go awry, it's fairly simple to go back and see what happened and to figure out kind of how you need to tune your data in order to make sure that the models improve over time. Unfortunately, most of AI and data science does not deal with models that are so simple. The linear regression, for instance, that you saw earlier, it always draws kind of a straight line, and then when you're trying to classify something, it kind of figures out which side of the line that you fall on, right? Classifiers, for all of their sort of mathematical complexities, are really just kind of fence builders. They take an input space which has a number of inputs. We could again talk about time of day and time of year, for instance, and then it figures out kind of a line drawn through the time of day and time of year, and which side of the line that you fall on kind of determines your classification. And so if you were to consider a classifier, just an arbitrary classifier, it doesn't really matter what it is, that is, we'll say complex, meaning that you can't really write it the way that we did the linear regressor right there, and inputs. We'll say kind of along the x-axis here, it could be something as simple as like time of day, and the y-axis here, I'm just going to go back to time of year. What will happen is you could create a classification of yes, no, true, false, that sort of thing. And what the classifier would do would be to take in all the input values for x and y, and it would draw a line. And it would be a very complicated line, curves, points, convex and concave areas to it, where inside of the line that's drawn, inside of the boundary, you would have one value, yes, and outside of that boundary, you would have the negative value, or the zero, or the false, whatever it is you're looking at. Now, those sorts of models, right? Things like neural networks, support vector machines, etc. They're incredibly powerful, and the reason they're incredibly powerful is because they can draw these boundaries internally in any sort of arbitrary way that they want, which is great for the AI's ability to solve problems, but it's really bad for practitioners of AI as well as end users in understanding how the classifier came about its decision. And the reason is because a classifier that's built like this cannot mathematically be written the way that we saw earlier, where it's just kind of the sum of a bunch of independent variables. And so a few years ago, there was a technique put together, and this is one of our current state-of-the-art techniques, called LIME, locally interpretable model agnostic explanations. What LIME actually does is that LIME takes a classifier, so one that can have any sort of arbitrary boundary, kind of like this, and then it looks locally in the vicinity of the endpoint, in the vicinity of the input that you want a classification from. Okay, and so if you're interested in why the classifier that we called F here decided that this X was kind of in the peach area, what you can do is you can take the input that was given to F, as well as this LIME technique. And what the LIME technique is going to do is it's going to blow up this little square area over to what we have on the right here, where's the figure 2, this kind of local view right here, where we have that X input that you were interested in. And what the LIME algorithm is going to do is that around that area, it's going to create an approximation to your original classifier. So originally you had kind of a curve going through here, and what LIME is going to do is try to approximate that curve as best it can by a boundary, just like a simple straight line fence. And then it's going to figure out, are you on the left side of the fence, or are you on the right side of the fence? And what changes to the input we had to accomplish in order to get you on the left side of the fence in the peach area, the right side of the fence. So all these little X's are kind of guesses at making small changes to your input. And then once this line is drawn, based upon those small changes and whether that put you on the left side of the fence or the right side of the fence, we can calculate these beta values like we did earlier, and then just look at the beta value that happens to be the largest to attribute essentially the blame for the classification one way or the other, right? The explainability. And so in the case of LIME, what happens is that we have a very complicated classifier that we then approximate in a very simple mathematical way around the area that we care about, and that allows us to identify what inputs had the biggest effect on the overall classification, regardless of what the classifier had to be, right? Again, this could be a neural net, it could be random forest, it could be whatever your favorite classifier happens to be. What's important is figuring out where you sit next to this line and kind of how far it is to the boundary, to that line from the input that you're interested in knowing the explainability, the input that you're interested in explaining. The second state-of-the-art technique that we're going to talk about real quickly is called gradient-based attribution. And so if you remember in the situations that I've talked about that were really explainable, the linear classifier and that kind of local explanation, what we were really interested in were kind of the beta values for either the model itself in a linear regression case or the local approximation in the LIME case. Those beta values physically are telling us how much the output will change if we change little bits of the input. Okay? And so for gradient-based attribution, what we do is we take input, we feed it into a classifier, and then we see how much the classifier's opinion about a classification would change if we changed one of the input values, not one of the input, as we change different input values. Now, using modern techniques from things like TensorFlow and PyTorch, this is a really straightforward thing to compute with some of what they call the AutoGrad modules. And you can see it kind of works pretty well in that this image is an image of an antelope. It's the way it would be classified. And that area is the area that we would consider to be most important just by looking at the sensitivity map, kind of based upon those gradients we just talked about. Where it fails is that it provides a very large number of outputs, and it doesn't necessarily hone in the specifics of the input domain, in this case, of the image itself. While this antelope is definitely in this area, so is all this prairie grass around it. In the same way that earlier you saw the picture of the husky that was being misclassified based upon all of the snow that happened to be around it. And so what we did at Monty was that we looked at both kind of the idea that you need to be able to get to decision boundaries, and you need to understand kind of how gradients are impacting the overall classification accuracy of a model in order to be able to explain it. And we saw a lot of synergies between that sort of explainability approach as well as what's called adversarial AI. You see, there's a series of, or there's a section of AI research that specifically hones in on trying to fool models, right? Trying to get a model that might be classifying a picture of a cat to turn that into, say, a classification of a dog. In order to do that, they need a lot of the same sort of information that you need in explainability. In our LIME example, we were kind of looking at how close we were to a boundary that was being drawn. And the adversarial AI folks, they're also trying to get to those boundaries. And so after evaluating kind of how the two relate, we developed an explainability capability we called AXAI, which leverages an adversarial attack known as a projected gradient descent. What projected gradient descent does is that it takes an input value that's being provided. This could be a picture, for instance, and then what it does is it adds in just a little bit of random noise associated with changes in the output of the image. Compared to the original image. So we take an image, we kind of add a little bit of noise to it, we see how that changes the outputs, and then we provide a new image based upon how successful or unsuccessful the changes we were at fooling the model at the end of the day. Right? And so when people try to use this technique in general, it's a way to try to fool models into making improper classifications. But in our case, what we did was try to use that same information in order to identify the parts or the input data that was most important to the overall classification of the model without sort of the nefarious ends associated with it. And so one example we have here is that we had a picture of a cat. Right? And so we fed in that original image of a cat, and then we ended up performing our projected gradient descent, our kind of attack, our adversarial attack on that image until we were able to fool the model, right, into believing that this wasn't an image of a cat, but that this was instead an image of a dog. And in order to do that, you actually have to make just kind of a lot of very small changes to the overall image. But once you make all those changes to the image and you manage to effectively fool the classifier from thinking that you have an image of a cat into, say, an image of a dog, what we do is that we go in and look at those small perturbations. We'll basically get rid of all perturbations that happen to be smaller than a particular threshold, right? So we attack the image. We identify the places in the image where the fewest number of attacks can actually lead to a misclassification, which allows us then to create an image that has only a few pixels that are changed, which will confuse the classifier, right? For an adversarial AI expert, this is the way they're going to go about trying to fool your classifier. It has the benefit of also being the identity and the location of the pixels that an explainable AI practitioner would want in order to be able to explain the image. So for us, we take the image, we perform the attack, we filter out kind of all the small perturbations from our attack, leaving only the biggest magnitude ones. And then once we've got our location for where all those magnitudes are, where the magnitudes are that we care about, we take the original image, we segment it into areas just sort of based upon the colors and the gradients and what belongs together in different areas, giving us kind of this segment map. And we then combine the two, keeping only the areas that had sort of the greatest impact on our classification ability, which provided us the possibility to generate an explanation. And so AXAI under the hood attacks the classification, identifies the areas of input that the model is most susceptible to, and then uses that to generate our explanation. This is something that works not only with imagery, as you can see here, for identifying why this model thinks this is an image of a deer, but also object detection, as it helps us to identify areas within the object or inner areas within an image that collectively form a particular or individual object, as well as NLP. It works across a series of modalities, as long as we have the ability to attack the model in some way, shape, form, or fashion. In terms of comparisons versus state-of-the-art, we've actually compared AXAI against LIME, we've compared it against SHAP, and a few others. The outputs from AXAI are very comparable in terms of accuracy, and so what you can see here is this was a picture of a gas pump, a praying mantis, and this other guy down here. And our AXAI capability goes ahead and pulls out, identifies as the area of interest the same area within the image that all of the current state-of-the-art capabilities are. So in terms of accuracy, AXAI is right there with current state-of-the-art applications. Where AXAI succeeds a little more than state-of-the-art applications is in its processing speed. When we've run benchmark tests against both single CPU as well as single GPU, AXAI has always come out to be faster. In the case, in kind of our best case scenarios, we're 16 times faster. And even in the GPU accelerated cases, we're around twice as fast. So in conclusion, AI is impacting our lives kind of on a daily basis now, and we need explainable AI solutions so that we can make sure that the decisions the AI systems are making are reasonable, so that when they're impacting our lives, we know that they're happening for reasons that we would agree with. Right? That's led to the emergence of kind of the explainable AI field, and Monty's AXAI solution is leveraging a new approach to that explainability problem that's competing well with state-of-the-art solutions, but just simply providing them faster. Anyone who's actually interested in the technical details of AXAI can take a look at the paper. It's available on arXiv for anyone to see. And I'm going to pause there and ask if anybody's got questions.
This is great, Clayton. Thank you for for both the mathematical and conceptual explanation of what's happening with explainability. Where do you see explainability and interpretability going in the future? I mean, do you have any sense as to how those two things are going to collide so that the average person can make sense of what models are doing?
Yeah, I think it's a difficult area, right? Because what people are always looking for is what people tend to be looking for, especially in the research community, are more and more accurate models, right? The problem is that the trade-off for the more and more accurate models is significantly more complexity. And in some cases, not just the complexity, but trade-offs for different input types. And so as you start making the models more and more complex, getting interpretability correct, right? Meaning the difference between just attributing cause to an input versus you being able to understand what that attribution means gets harder and harder. And I think I've used as an example before. If someone were to build an object classifier, it's pretty easy to explain to people that this pixel group here corresponds. This pixel group here was the reason that your classifier made this particular decision, or the object detector made a decision that there was a car in this location, or there was a boat in this location. But when the input data isn't necessarily human interpretable, things like SAR radar, for instance, then it becomes a lot more complicated to help people understand why the machine learning model made the decision, even if you can mathematically attribute it. And so as the sort of models get more and more complicated or deal with more sort of abstract data sources, the sort of gulf that you have between not just being able to attribute something, but also being able to understand something, I think will continue to grow, which will go ahead and open up a brand new area of academic research, right? I mean, that creates a new problem, which is going to entice people who are interested in that problem to go ahead and tackle it and try to help kind of close that gap back up that kind of as it emerges.
That makes a lot of sense, Clayton. Thank you so much. I got to run, but that was a great answer.